Hello everyone, welcome to electronics tutorials. In this video, I am going to discuss on center tapped full wave rectifier with a resistive load. Let me start the discussion with the definition for a rectifier. A device that converts alternating current, that is AC, to direct current, that is DC, is called as a rectifier. In general terms, we call AC to DC converter as a rectifier. In my previous video, I have discussed a half wave rectifier with a resistive load. There we learned that a half wave rectifier converts AC to DC only during one of the input half cycles. Since that particular technique creates a lot of power loss at the output, we go for the next one, which is the full wave rectifier. So what is the definition of a full wave rectifier? A full wave rectifier is an AC to DC converter that converts the input power into output power in both the positive as well as negative half cycles of the input supply. That would be the generic definition. So what is this center tapped full wave rectifier? The definition of a center tapped full wave rectifier is a device that uses a center tapped transformer and converts AC to DC in both the half cycles of the input supply. So it is as good as saying it is a full wave rectifier, but here we use a transformer that is center tapped. Let us now understand what is a center tap. Basically, you should understand, in electronic terms, a center tap is nothing but a contact made to a point halfway along the winding of a transformer or an inductor or along the element of either a resistor or a potentiometer. This contact is called as a center tap. Finally, we should also note that since a rectifier converts AC to DC, it is also called as an AC to DC power converter. Let us discuss a little bit more on center tap transformer. On the left here, I have shown the diagram for the center tap transformer. You can see the left winding is the primary winding, the right winding is the secondary winding, and in the middle of the secondary winding, you can see there is a green color line. That is a wire that is connected to the midpoint of the secondary of the transformer, and this contact is called as a center tap. So we can now say when an additional wire is connected across exactly the middle of the secondary winding of the transformer, then it is called as a center tapped transformer. So what is the advantage of this center tapping? With center tapping, we can split the secondary winding of the transformer so that you can now take two output socket outlets from the same secondary winding. Lastly, another very important thing you should note about the center tap is that it should be grounded. That is, the contact point between the wire that is shown in the green color here and the midpoint of the secondary should be grounded. Let us now start the discussion on the center tapped full wave rectifier, and the circuit diagram for the same is shown in figure 1 here. Please note, we have used a resistive load. The circuit consists of a transformer with a primary voltage equal to Vp, secondary voltage equal to Vs. You can see the secondary voltage Vs is shown both in the top as well as the bottom circuits across the secondary. We have two diodes of very similar characteristics. Let the diode in the upper path be called D1 and the one in the lower path be called D2. And lastly, we have a resistive load. Here we have denoted the voltage across the diode D1 as VD1 and voltage across the diode D2 as VD2. Please note, they both represent instantaneous voltages across the anode and cathode terminals of the diodes. To understand the working of the center tap transformer, we need to analyze the circuit behavior both in the positive as well as the negative half cycles of the input supply. So, I will be now splitting my discussion into positive half cycle and negative half cycle. In fact, I have created two separate circuits indicating which switching device will be on and which will be off during the positive as well as negative half cycles. Let me start with the first one, which is during the positive half cycle of the input supply. Figure 2 here shows the circuit equivalent of our previous circuit during the positive half cycle of the input supply. It should be noted that during the positive half cycle, the secondary transformer voltage Vs is positive at the top and negative at the bottom. The same is also true for the bottom circuit of the secondary winding. Because of this way of voltage appearing across the secondary winding, the diode D1 will have a positive voltage across its anode and a negative voltage across its cathode. This voltage combination is sufficient to forward bias the diode, assuming we have considered an ideal diode. So, that is why in this diagram I have shown diode D1 to be closed and the voltage VD1 is equal to 0 because the diode is forward biased. Coming to the diode D2, we now note that the anode of diode D2 is actually at a negative potential, whereas the cathode is at positive potential. This voltage combination will reverse bias the diode D2 and therefore diode D2 will be open circuited. That is what is shown here. Now, since the diode D2 is open circuited, the voltage across the diode D2 during the positive half cycle of the input supply will be equivalent to the input voltage itself. Let us now discuss about the output voltage and output current. Since the lower diode is off, let us not consider that branch for the analysis at all. I will only be considering the circuit formed between diode D1 and the load resistance R. Since we are analyzing the circuit during the positive half cycle of the input supply and the diode D1 is forward biased, the current direction will be from anode to cathode. So, this will be the current direction during the positive half cycle of the input supply. Let us consider this current direction as a positive current direction. It is a convention and that is what we will be assuming. Coming to the output voltage, you will note that the right side edge of the load resistance is connected to the positive terminal of the secondary and the left side edge of the load resistance is connected to the negative terminal of the secondary. This is also shown with this polarity here. So, the output load voltage during the positive half cycle of the input, assuming a lossless diode, equals the input voltage across the same period. That is, the output voltage V0 when D1 is turned on is equal to input voltage Vs. Therefore, when diode D1 is closed, the output voltage and output current are both assumed to be positive. This is our analysis on the circuit behavior during the positive half cycle of the input supply. Let us now move on and analyze the circuit behavior during the negative half cycle. Figure 3 here shows the circuit equivalent during the negative half cycle of the input supply. It should be noted that during the negative half cycle of the input supply, the upper branch will have negative polarity voltage and the lower branch will have positive polarity voltage. And accordingly, this point will be positive and this would be negative. Therefore, now for diode D1, a negative voltage is applied across the anode and a positive voltage is applied across the cathode. This voltage combination will reverse bias diode D1 and therefore diode D1 will become open circuited. And as we have previously discussed, when a diode is reverse biased, the voltage across the diode is equal to the supply voltage. So, VD1 is equal to Vs during the negative half cycle of the input supply. Coming to diode D2, you will note that the anode of the diode is now at a positive potential and the cathode is at a negative potential. This voltage combination will forward bias the diode D2 and it becomes closed circuit. When the diode is closed, the voltage across the same is equal to 0 volts. So, in the negative half cycle, diode D1 is open and diode D2 is closed. Let us now discuss the output voltage and output current. Now, I will only be considering the lower branch because diode D1 is open. When diode D2 is conducting and since diode is a unidirectional device, the current flows from anode to cathode, that is in this direction. So, the current direction across the load when diode D2 is conducting is the same exact as when the diode D1 was conducting in the positive half cycle of the input supply. That means the current direction has not changed in the negative half cycle of the supply. Further, coming to the output voltage, you will once again note that the right side edge of the load resistance is again connected to the positive terminal of the secondary, and the left side edge of the load resistance is connected to the negative terminal of the secondary. Therefore, the load voltage continues to have the same polarity as what was seen across the positive half cycle of the supply. So, we can now say that the output voltage and the output current have the same polarity as what was seen in the positive half cycle. That is the analysis of the circuit behavior in the negative half cycle of the input supply. Let us now move on and discuss the waveforms for the center tapped full wave rectifier. Here I have shown a set of waveforms indicating the input voltage, output voltage, voltage across diode D1 and voltage across diode D2. I will be starting the analysis with the positive half cycle of the input supply, and I will be considering each of these waveforms individually. During the positive half cycle of the input supply, that is between the period 0 and pi, we note that diode D1 is conducting and D2 is off. And we have already analyzed that during the diode D1 conduction, the output voltage follows the input voltage and the output current is positive. So, when you come to the second waveform here, which represents the output voltage, you will note that between the period 0 to pi, which indicates the positive half cycle across the input, the output voltage, which is shown in the pink colored waveform here, is exactly the same as that of the input voltage, which is the first set of waveform here between 0 and pi. This indicates the output voltage and input voltage are equal to each other during the positive half cycle of the input supply. Talking about the output current, since we have assumed a resistive load here and in a resistive circuit voltage and current are in phase with each other, the current waveform will have the same shape as that of the output voltage waveform, only that it will be of lesser amplitude. This reduction in amplitude is because of the value of the load resistance itself. If I assume Vm to be the peak value of the input voltage, then the peak value of the output voltage will also be equal to Vm, assuming a lossless diode. On the other hand, the peak value of the output current will be equal to Vm divided by R. That is the relation between output voltage and output current. Let us now move on and analyze the waveforms for the negative half cycle of the input supply, that is between pi and 2 pi. As previously discussed, during a negative half cycle of the input supply, diode D1 is open whereas diode D2 is closed. However, while analyzing, we have learned that the output voltage and the output current are once again positive in the negative half cycle of the input supply as well. This is quite expected because this is an AC to DC converter and therefore the negative elements of the AC are supposed to be eliminated. Also, since we have assumed ideal diodes and ideal diodes does not require any voltage to turn on, the output voltage across the load during the negative half cycle of the input supply is equal to the input voltage except for the negative polarity. That is, the voltage across the load between the duration pi and 2 pi is exactly the same as the voltage across the load between 0 and pi. This we must understand is because of the way in which the circuit is constructed. We have constructed the circuit to convert AC to DC. Therefore, the negative half cycle of the AC will be completely eliminated. So, we now learn that the output voltage remains exactly the same between 0 to pi as well as pi to 2 pi. A very similar principle can also be extended to the output current. The output current during the positive half cycle of the supply and the negative half cycle of the supply remain exactly the same. Well, that is the analysis on the output voltage and output current. Let us now look at the waveforms for the diode D1 and diode D2. We have learned that diode D1 is forward biased during the positive half cycle of the input supply. Therefore, during this duration, the diode D1 will be a closed circuit. And an ideal closed circuit will exhibit no losses as what we have assumed for the diodes itself. Therefore, the voltage across the diode D1 during the positive half cycle of the input supply will be 0. This is shown with a flat line from 0 to pi across the diode D1 voltage, which is our third set of waveform here. Coming to the diode D2 during the same period, we have said diode D2 is open circuited during the positive half cycle of the input supply. Since it is open circuited, the voltage across the diode D2 will be equal to that of the supply itself. However, since the diode D2 is connected in such a way that the voltage appears negatively across the diode D2, the positive half cycle of the input supply will appear negatively across diode D2. This is what is shown between 0 to pi on the last waveform here, which is for diode D2. So, the voltage across diode D1 during the positive half cycle is 0 and the voltage across diode D2 is simply minus Vs. Coming to the negative half cycle, the same principle is now applied across diode D1. That is, in the negative half cycle of the input supply, diode D1 is open circuited whereas diode D2 is closed. So, the voltage across the diode D2 between pi and 2 pi will be 0, whereas the voltage across the diode D1 will be minus Vs. This can be seen between pi and 2 pi for diode D1 and D2 voltage waveforms respectively. That is the analysis of waveforms for a center tapped full wave rectifier. Let us now move on towards the mathematical analysis of the center tapped full wave rectifier. I am going to start the mathematical analysis by deriving an expression for the average output voltage. The average output voltage of a full wave rectifier is equal to the DC component V0 and is given by V0 equals 1 divided by 2 pi integral 0 to 2 pi V0 omega t d omega t. Let us now understand how this equation is constructed. Let us go back to the waveforms for the output voltage now. Now look at the output voltage here. The period of operation is 0 to 2 pi. That is why when I start writing the equation, I start it by 1 divided by 2 pi. Then we have the waveforms continuously varying from 0 and 2 pi. This makes the signal a continuous signal. And whenever I want to find a value of a continuous signal, I have to integrate it. That is why we have taken integration. And since the overall period of operation is 0 and 2 pi, the integral limits will be 0 and 2 pi. Lastly, we need to now write the quantity that is being integrated, which is V0 itself. So, the equation for the average output voltage is 1 divided by 2 pi integral 0 to 2 pi V0 omega t d omega t. Now, since we see the output voltage appears both across the positive as well as negative half cycles of the input supply, I will split the integration into two parts. The first one will be between 0 and pi, which is shown in the first part of the equation here, and the second one would be from pi to 2 pi, which is shown here. Let us now move on and find the value for V0 omega t. During the positive half cycle of the input supply, the output voltage is equal to input voltage, and that is why V0 omega t here is replaced by Vm sin omega t in the next step. Coming to the second integral, which is from pi to 2 pi, we now note that the negative half cycle of the input supply is converted into positive half cycle. So, V0 omega t during the negative half cycle of the input supply is equal to minus Vm sin omega t. Please note, this is because the negative half cycle of the input supply is converted to the positive half cycle during the period pi to 2 pi. That is why we should write it as minus Vm sin omega t. In my next step, I am going to take Vm constant and I am going to write it here. So, the constant term would be Vm divided by 2 pi. Then let me integrate sin omega t. Integration of sin omega t is minus cos omega t. Therefore, here I have written minus cos omega t and then I have the limits 0 and pi. The same is also done for the second integral. So, it is once again minus cos omega t, but the integration limits should be from pi to 2 pi. Please make that correction here. In my next step, I will apply the limits. So, the first term here will become minus of cos pi minus cos 0. Then we have the minus here and minus here. So, therefore, this will become positive. So, then we will have cos 2 pi minus cos pi. So, minus is retained here. cos pi is minus 1, cos 0 is 1. Coming to the second term, cos 2 pi is plus 1, cos pi is minus 1. Therefore, this reduces to Vm by 2 pi multiplied by 2 plus 2, that is nothing but Vm by 2 pi multiplied by 4. So, the final expression for the average value of a full wave rectifier is V naught equal to 2 Vm by pi. Please note, this is exactly the double as what we got for a half wave rectifier. Let me now continue and find an expression for the RMS value of the output voltage. The RMS value of the output voltage is denoted by Vrms. So, now I need to simply modify my previous expression, that is for V naught. I have to simply now square the contents that are being integrated and put a square root over the complete thing. So, it will be 1 divided by 2 pi integral 0 to 2 pi V naught square omega t d omega t whole to the power 1 by 2. Now, I am going to once again split the integration between the limits 0 to pi and pi to 2 pi. Then I am going to substitute for V naught omega t during each interval. During the positive half cycle, that is from 0 to pi, V naught is nothing but Vm sin omega t, then we have a square. And in the negative half cycle, that is between pi to 2 pi, V naught is minus Vm sin omega t, then we have a square. The square here is very important to note. Now, if you look at the second part here, you will note that minus Vm sin omega t whole square will eliminate this minus symbol. So, this will be as good as writing Vm sin omega t square. So, what we now have under each integral limits is nothing but Vm sin omega t whole square. Therefore, in my next step, I will reduce the two integrals into one single integral by introducing 2 multiplied by term. So, the two integrals in the previous step can be reduced as 2 multiplied by integral 0 to pi Vm square sin square omega t d omega t. Now, I will be cancelling out this 2 and this 2 here, and Vm square is taken to the constant side. So, it will be Vm square divided by pi. Then we have the integral 0 to pi. We know that sin square omega t cannot be directly integrated. So, I will write it in terms of the cos as 1 minus cos 2 omega t divided by 2. In my next step, I am going to take this 2 to the denominator here. So, the constant term would be Vm square divided by 2 pi. I am going to now multiply d omega t into 1 minus cos 2 omega t, and I am going to write the integral limit for individual components. So, it will be integral 0 to pi d omega t minus of integral 0 to pi cos 2 omega t, then we have the rest of the components retained as it is. Let us now integrate. It will be Vm square divided by 2 pi. Then integration of d omega t is omega t and the limits are 0 to pi. Coming to the next step, integration of cos 2 omega t is sin 2 omega t divided by 2, which is written here, and the limits are still 0 to pi. Let us now apply the limits. Omega t between the limits pi and 0 will be pi minus 0. Coming to the second term, we will have sin 2 pi minus sin 0 divided by 2. In the next step, let me substitute the values for sin 2 pi and sin 0. Sin of any pi is 0, so it will be 0. Sin 0 is also 0. So, the complete expression within the curly braces here, it will reduce to pi. I will cancel this pi here. So, what remains is Vm square divided by 2 whole to the power 1 by 2. Therefore, the final expression for the RMS value of the output voltage is Vm divided by root 2. Moving on, the average output current of the full wave rectifier is equal to the DC component I naught and is given by V naught divided by R. V naught here is the average value of the output voltage, and we have previously derived this to be equal to 2 Vm by pi. Therefore, I naught will be equal to 2 Vm by pi into R. In a very similar fashion, the expression for the output RMS current IRMS is equal to Vrms divided by R. Vrms is Vm by root 2, therefore, IRMS is Vm divided by root 2 into R. Further, the average power produced by the input supply is given by Pi equals Vs into Is. Vs here is the RMS value of the input voltage, Is stands for the RMS value of the input current. Then the average power absorbed by the load is given by P naught equals Vrms into Irms. Therefore, the power factor of the full wave rectifier can be given as Pf equals Vrms Irms divided by Vs into Is. That is, it is the ratio of the average power absorbed by the load to the average power produced by the input supply. Next parameter I will be analyzing is the ripple factor. Ripple factor determines how well a rectifier converts AC voltage to DC voltage, and it is given by the expression Rf, which stands for ripple factor, equals square root of Vrms divided by V naught whole square minus 1. We have previously derived Vrms as Vm by root 2 and V naught as 2 Vm by pi. That is substituted in the next step here, and after simplifying we find the ratio of Vrms by V naught as pi divided by 2 root 2. Then simplifying and calculating for Rf, we will obtain the ripple factor for the center tapped full wave rectifier as 0.4834. Let me now discuss the efficiency of the rectifier, which is also called as the rectification ratio. We should note that the efficiency of a rectifier is the ratio of the output DC power to the input AC power. It is represented by eta and is the ratio of PDC divided by PAC. Now, PDC can be written as I naught square divided by R and PAC can be written as IRMS square divided by R. Let us cancel R here. So, what remains is I naught square divided by IRMS square. We have previously found the expression for I naught as well as IRMS. I naught is equal to 2 Vm by pi into R and IRMS is equals to Vm by root 2 into R. So, substitute and simplify this, you will obtain eta to be 8 divided by pi square, which simplifies to 0.8105 or simply 81.05%. Please note, this is the maximum achievable rectification ratio for the center tapped full wave rectifier. Moving on now to the form factor. We should note that form factor is a measure of the shape of the output voltage and it is given by the expression Ff, which stands for form factor, is equal to Vrms by V naught. Vrms is Vm by root 2, V naught is 2 Vm by pi. Simplifying this, we will find the form factor for a center tapped full wave rectifier to be 1.1107. Lastly, I will be considering the transformer utilization factor. The transformer utilization factor of a rectifier circuit is defined as the ratio of the DC power available at the load resistor to the AC rating of the secondary coil of the transformer. So, TUF can be written as PDC, which is the DC power at the load, divided by Vs into Is, which is the AC rating of the secondary coil of the transformer. Right. With that, we have completed the mathematical analysis of the center tapped full wave rectifier. Let us now move on and discuss the advantages of this circuit over the half wave rectifier and then its applications. I am going to start with the advantages of the center tapped full wave rectifier over the half wave rectifier. The first and foremost important advantage is the full wave rectifier has higher efficiency compared to that of the half wave rectifier. For the half wave rectifier, we have noted that the efficiency is around 41%, whereas for the full wave rectifier, it is almost double of that value. Coming to the second advantage, a center tapped full wave rectifier converts AC to DC in both half cycles of the input supply. Therefore, there will not be any loss in the output power. Coming to the third advantage, as both the input cycles are used in the rectification, there will be no loss in the input voltage signal. Moving on, the ripple factor of a full wave rectifier is considerably less compared to that of a half wave rectifier, which indicates the full wave rectifier output produces a better DC output than the half wave rectifier. Lastly, a full wave rectifier has a higher value of the average voltage V naught compared to that of the half wave rectifier. These are the advantages of the center tapped full wave rectifier over the half wave rectifier. Let us now discuss the disadvantages of the center tapped full wave rectifier. It should be noted that we have two diodes here, and each diode conducts only during one of the half cycles of the input supply. Therefore, each diode utilizes only one half of the voltage developed across the secondary of the transformer, and thus the DC output obtained is considerably small. Coming to the second disadvantage, it is quite difficult to locate the center of the secondary for tapping. Please note, we have used a center tap transformer and center tapping is quite difficult. Moving to the third disadvantage, the diodes that are used here must be capable of bearing a very high peak inverse voltage. Each of the diode in this center tap transformer will have to bear a peak inverse voltage of minus 2 Vm, which is twice the maximum voltage across half of the secondary winding. Coming to the last part of this discussion, we have the applications. Center tapped full wave rectifiers are employed in AC to DC transmissions. Further, because they have enhanced efficiency, they are also used in power supply units. Lastly, they are also used in the context of functioning of some of the equipment such as LEDs or motors. These equipment commonly use rectifier circuits. Right. With that, we have come to the end of this video. If you found this video to be informative, kindly like and share this video and subscribe to my channel for more information on electronics tutorials. Thank you for watching. Have a good day.